let's talk about periodic trends. This is section 6 in chapter 3 and is part 3 of the lecture series. As we mentioned before, the periodic table is organized in such a way where we have rows and columns of these elements, and if we are looking at columns of elements, they are organized in family groups, as we said earlier, and they share similar characteristics and so on and so forth. We also can observe certain atomic trends as we move around the periodic table. And there are several different ones, but we're only going to talk about a few for this chapter. The first of the ones that we're going to talk about is the atomic radius. And how does it change with going across the periodic table or down a group, etc. So if I'm looking, here I have an example of the halogens. The halogens exist as diatomic molecules. So F2, Cl2, Br2, I2, etc. And the radius is defined as half the distance between their two nuclei. And as you see, as I'm going from fluorine all the way to iodine, that radius starts to increase. That is the general trend. As I'm moving down a group, so from fluorine moving down towards the iodine, I see that the atomic radius increases. What I also see is that if I move across the row or the period from lithium towards fluorine, the atomic radius decreases. Now, the easiest way to remember this, I always think of it this way. If you remember the one that has the largest atomic radius, whatever direction you're moving is going to decrease. So if I remember that francium here has the largest atomic radius, if I'm moving across, so away from francium, from left to right, across the row, the radius is going to decrease. And if I move from bottom up in a group, the radius is going to decrease. So if I remember that francium has the largest radius, no matter what direction I go, so from bottom up in a group or left to right, the radius is going to decrease. And here's the same idea. Going from iodine to fluorine, I'm moving from the bottom up, which means that I'm decreasing the radius. Now let's talk about why this is so. Well, or let's talk about why it increases as we go down a group. What we're doing is we increase, as we go down the periodic table, we increase the atomic number, which means that we increase the number of protons as well as the number of electrons that are orbiting these atoms. And as we said, as we increase the number of the period here, we increase the shells around the electronic shells around the nucleus in which the electrons could be found. And because that is part of how we determine the radius of the atom, that means that the more shells you have, the lower you go in the periodic table, the more electronic levels you have, the larger that radius is going to be. Now across, so this is going down a group, it increases. If you go across, it decreases. Why is that? Well, that's because the electrons kind of are held tightly by the nucleus, because what we're doing is we're increasing the number of protons, but we're not increasing the energy levels. Even though we're balancing the electrons with the protons, those electrons are still found in the same energy level and therefore in the same sphere around the nucleus. So even though we're balancing them, the total charges, that those electrons that we're filling here are feeling the full effect of all of the protons in the nucleus. Now, as we go to the next shell, we increase the distance in which those electrons are found from the nucleus. And so they don't quite see the effect of all the protons because they're kind of shielded. We call them shielding. They're kind of protected from these inner electrons a little bit because they take the brunt of that attraction. And so the further out we go, the less attraction those electrons are going to feel from those protons inside. And so we see that the size increases here, but it decreases as we go across within the same energy level. Now let's talk. Well, here's kind of a depiction of the elements by groups, radius and the atomic number. As you can see, this is my group 7. And as I go down, so helium is the first, the highest. Helium is up here, helium. So as I go down a group, this is what happens. The radius increases. As you can see, this is increasing as I'm going down, even though this doesn't appear down, but helium is first, then below it is neon, then argon, then krypton and xenon. This is the noble gas, and you're going down in energy levels, but the radius is increasing. Same thing here with lithium group 1 elements. Lithium is the smallest, and as I go down the group, the radius increases, going to cesium. And then francium is even larger, but it's not as stable. Now in between they follow the same idea, but there's a little bit of a few very small exceptions to the rule, but we're not going to talk about that. In general, though, if you have atomic radii, if you follow the trend, it's going to follow this way, that as you go across the period, the energy level, it's going to decrease, and as you go down a group, it's going to increase. Okay, that's the atomic radius. Now let's talk about the ionization energy. The first ionization energy is the energy that we need to supply to the atom for it to lose that first electron to become a positive ion, +1 charge. So it's a measure of how easy it is for an atom to lose that first electron. And as you can see, the group 1 over here has the lowest first ionization energies, and group 8 or 18, so the noble gases, have the highest values. That's because we said they are noble gases, they have full configurations, their electronic shells or their orbitals are full, they are very unreactive, and it takes a lot of energy to make them lose that electron. So here's the trend. Once again, if you remember that helium has the largest ionization energy, anything in each direction, so going down from helium or from helium to the left, it's going to decrease. Or if you think of francium as having the lowest, it's going to increase as you go above and across. Now, why is that? Once again, these group 1 elements, we said they want to lose that electron to get to the configuration of the noble gases. It's easy for them to lose that one electron than it is to gain all of those. So they only have one electron to lose, and it's very easy to do so. Whereas when we get to helium, it has to lose, well, to this group anyway, helium has to lose 1, but neon has to lose 7 electrons to get to the same configuration as lithium. So it's very difficult for neon to lose an electron because it has a full shell and it likes that full shell. So all of the noble gases have full electronic configurations, they have full orbitals, and they do not like to lose those electrons. That is why they have the highest levels. Helium has the highest out of all of them because those electrons are so close to the nucleus that they are held very tightly. Whereas as you go, once again, the radius of the atomic radius increases as you go down a group. So those electrons that are really further away from the nucleus, they're not held as tightly as those that are much closer, like the helium's electrons, and therefore they're easier to lose. Although even though they're easier to lose than helium, they're not as easy to lose because look at it has double almost it requires double the energy to lose the first electron than it does for lithium, etc., etc. So the ionization energy trend is if helium has the highest, then anything else will decrease in either direction. And here it is. So once again, if I'm looking at this is the group, not a group 8, so it's the noble gas configuration. The ionization energy here versus the atomic number. So the ionization energy, helium has the highest, and then neon, argon, krypton, and xenon, etc. So as I go down a group, it decreases somewhat. And once again, even here, as I go down a group, it decreases. As I go from lithium, so from lithium all the way to neon, so across a period, this is across a period, the ionization energy in general increases. That is the trend in ionization energy. Remember, it is the energy that it's needed to be, it's supplied, so it's needed for that element to lose the first electron. That is the end of the atomic trends that we're going to talk about. There are more, but we're only going to talk about those right now. And we're going to pick up in part 4 with ionic compounds and how to figure out how to make positive ions and negative ions and use a periodic table to predict what type of ions that particular element will form.